it's great, like you're getting introduced like a WWE superstar. And I see everybody's like, who? So let me shed some light into the who, so that after this presentation, next time you hear that introduction, you're like, ah, that guy. All right, empowering Silicon Valley teams to shorten delivery timelines of complex systems by applying continuous validation methods. So that's a mouthful. The good news is that was the most complicated part of my presentation. I just tried to put as many buzzwords as possible in there, which I think I succeeded. Anyway, let me quickly introduce myself. I started as an intern at Bosch back in the day in Germany, working on some algorithms for rollover protection. Started as a validation engineer as a junior, company called Siemens VDO. We were working on the first generation electric power steering system. So ACLD project, one of the first going outside of the e-gas, was pretty challenging. For Volkswagen. The company then got bought by Continental, and I requested my delegation to a more interesting spot, so I went to the country of Romania for 4 years and built up a location over there to the very, very east of the European Union, so we were able to walk out of the European Union. So 2012, I thought I need some challenge. So I went and I started to work at a company. It's called Tesla. Back in the day, Tesla Motors. And they just sold a few hundred Model S cars. So I arrived there, and they explained to me, so far we don't have a validation team. Our engineers know what they're doing. So we don't need that. So they had an integration team, and that was basically taking care for the whole release process. So at Tesla, I found a team that was responsible for the software release on the vehicle. So all software that runs on Tesla vehicles, my team was responsible to release that as a package to the end customer. So we built great regression test capabilities, and we were able to reduce the delivery times down to hours. So from software commit, entire vehicle regression tests, including autopilot functionality, into the customer car or the other end of the world within hours. My presentation mainly deals with approaches I learned about in that time frame. But it's not explicitly Tesla content. After Tesla, I spent a year at NEO as the director of system integration and validation, mainly responsible for writing the validation strategy for level 4 autonomous vehicles. This summer, I decided I want to do something on my own. So I joined a very small consulting company called iProcess, so it goes all the way down here. That actually belongs to the presentation now. So iProcess, which also has an I in front, even though it's not a company of the 90s. I don't know where Jeff is. But. Very short summary of what we are doing. So we are consultants who actually did that stuff. So we don't consult by the book. We consult by the pain we had with dealing with the issues in the real world. We pretty much cover the entire V-cycle process-wise, including how we link things together. And it is mainly about automotive software on complex mechatronic systems. We also dip our feet a bit in like aerospace industry, maybe medical, but our main focus is our experiences in automotive. So we design processes, but we also help to improve processes. We help with strategy, implementation, integration support. Pretty much everything you need in order to get your product from an idea to an actual product in a customer hands, and furthermore. All right, so the challenge. I'm pretty sure you all saw those pictures 100 times. I randomly just put them there. It's not really a lot of details I want to go into, but you have a ton of different controllers in the modern car. I don't know the latest numbers, but it's somewhere 60, 80, maybe it's 100 now. And you have tons of lines of code. People like to compare the modern car to a space shuttle, or the Apollo is not even on that chart. It's a gigantic amount of software working on a lot of hardware in a car. So in my experience, all those teams, all those component teams do a pretty good job making sure that their component is doing the right thing. But Most issues in corner cases are actually integration problems. So the software in each controller does the right thing, but there's some sort of problem that shows up under certain conditions, certain environmental conditions, or certain cases, use cases that were not considered when the system, the architecture was designed. So my statement is, even with a well-designed or very well-designed system architecture with such a complex system, you will miss cases. I assume that everybody here, you found a little problem in your car, a little bug, and you say, okay, because I'm using my radio or whatever in this special way, I probably found a corner case they didn't consider. So how do they detect integration problems in the field? So when I say in the field, I'm referring to the customer, so you, I, not anybody who has a direct feedback line into the development. And how to react to the problems we found there. So I think I have to point that way. Answer for the question number one, an answer. I originally had like the answer, but I don't have the answer. I have only one answer, one I went through and I found sufficient. Implement a smart system to harvest data from your fleet and run alert algorithms, AI. This is not the content of my presentation. I'm happy to talk about that, but this is not today's content. The next point is, you have to create a fully integrated end-to-end system integration regression test landscape. That's another long wording, but it's pretty much what Jeff said on a system level. So end-to-end test automation. End-to-end test automation. Test automation or test execution in general always follows this diagram. So you always have a specification, you have some sort of schedule, some execution or evaluation, and some sort of report. To achieve real end-to-end test automation, you need to have the entire chain in place and automated. Different levels, when I speak about levels here, I'm talking about component, subsystem, and system and vehicle level, different levels. They may have different solutions for each step. But it is important for this concept that you agree on the interfaces between those steps. And the best solution for each level can be implemented if you decide to force feed test execution software into your organization and you tell everybody from component level test all the way to system level test, you have to use that solution. You will never reach total satisfaction in that team. I recommend specification and reports should be similar for all the levels, because in the end, you have a requirements engineering group. They will provide you the inputs. They should have a common tool. And the report should be something that is summarizing all levels of validation. I will go into the next slides. I will go into details of each of those boxes. So first, requirement specification. So this is not a complete list of options. This is a list of things I worked with and I'm capable of talking to you about. So for specification of requirements, you have the three classics. You have IBM Doors, Polarion, JAMA Contour. I worked with all three of them. They are off the shelf. I've seen very often used the following, but I totally don't recommend it. Any version of Microsoft Office is not good for requirement specification. I've seen a lot of requirements engineering in Confluence, which is okay if you design a simple website or something like that. But as soon as you get to a big configuration management and a highly complex product, I recommend not to use Confluence for that. PDFs are usually handed over by OEMs down to suppliers. I worked for a tier 2 supplier, and I said it's not very handy to get your requirements in PDF. I've seen other approaches lately in Silicon Valley, Git. So have your requirements together with your source code. The advantage is you branch with your source code. Your configuration management is handled by Git. You don't have to deal with that. The disadvantage is it's really hard to sell this to mechanical design and hardware engineers because they don't know what Git is. Product as a spec is something I've seen mainly in UI design. The UI people always told me I'm not writing down specification and then I design my UI. I design my UI and then you can look at it. So this is that. Test specification. So all those requirements management tools come with some sort of test specification and management option. On top of that, there are a few others. TestRail is one of them. I personally like to work with X-Ray, which is a plugin for Jira. Has the advantage that you don't have to train your engineers, because most of them know how to use Jira anyway. Frequently used but not recommended. Again, any kind of Microsoft Office documentation is not urgently a good idea for test management. Same with Confluence, PDF. Source code is something that is really shrugging me, because test engineers without a test specification, what they do, they read the source code and then test against what they read in the source code, which basically means they're validating the compiler. Never seen that? All right. So now about the actual test automation. So no matter if you automate or not your tests, you will have a scheduler. In the simplest way, this is the manager telling an engineer or technician, can you please test this today? So test is scheduled. What we implemented a lot at Tesla and at NEO is we use a CI server. In this case, we use Jenkins, but you can also use Bamboo or anything else. Because the software build machine is using a CI server. So it is very handy just to integrate your test automation with that very same CI server or a similar server, and they communicate to each other. So like this, you already solved the issue of how to trigger your test. For the execution, well, as I said, it can be manual. It's the least efficient, but in some cases it has to be manual. Sometimes humans are still better than machines. So there's a bunch of off-the-shelf tools. I added Canoe here at the bottom for this conference as well. Joke is, I use Canoe quite a lot. For the evaluation, so manual evaluation is what I see most. It's time-consuming. So you have the test execution running, and then in the end, somebody is looking in Canopy or whatever, looking at the graphs and say this is good, this is not good. Most of the execution tools I mentioned earlier offer some sort of evaluation as well. It's usually very digital. Sure, you can put in some tolerances, but in the end you have to put quite some effort in those tools in order to make them smart enough. I've seen a lot of great ideas, but not anything implemented yet to use some sort of AI to go through, especially when you have a high frequency of test execution. So you're running like your component tests like 20, 30, 50, 100 times a day. You might get drifts in your test results. And humans, and also those standard executions, they will only see that very late when you actually go over the threshold. But if you have some AI implemented in that, you can see how the drift starts, and you can put countermeasures much earlier in the process. All right. Reporting. So within the test management tools, you get a report. So if you are using IBM Rational, it has a report. If you're using any of the other tools, they have sort of report. But in the end, there's some sort of management above you that makes a decision if you're shipping that product or not. And in my experience, that level of management usually does not want to learn how my test management tool works. And so it then came out with the idea like, hey, let's do email subscription. So my boss gets an email every time I ran a test. This is great, but after the first 10,000 emails, they probably put you into the spam folder, and they will never see the actual important information. So what we came up then is, is a production-like dashboard idea. So most of you probably seen a production floor before. So you walk through a production floor, and every station has a big screen on top, and it basically shows you a color, red or green. If the color is green, you walk by and you said, everything's okay here. If the color is red, you, as a manager, probably stop and say, what's the problem? What can we do? So we did the same for software testing. So the software is testing, the test system is testing the software and is posting the results into a database that's shown on a dashboard. So in reality, what happened is most of the code commits, in my experience, happen somewhere at like 7 to 10 p.m. I don't know, it's somehow the time software developers work. That would mean that the test engineers would start to work somewhere between 10 p.m. and midnight. So we set our test system up in a way that it picks up those software changes and is running through the tests overnight. And then you come in into the morning with this gigantic TFT screen where the VP can see it. So if everything is green, you know it's a great day. If you come in and you have one red bubble, then it's like, oh, okay. It happens sometimes, everything is red. Then you have a bad day. All right, anyway, so the options listed here are some I worked with. Some of them are free, some of them cost money. All of them have one thing in common: you will need an engineer to maintain that. No dashboard option is no maintenance. Every dashboard option you need to have an infrastructure engineer working on it. All right, so continuous validation is empowered by two key methodologies. First, keep your change content as small as possible. Because if you have a test failing and you have 1,000 software commits in there, you are going to play Sherlock Holmes and you try to figure out what is actually the actual problem. And as I said earlier, most of the time you have integration problems. So it's not that easy to say, okay, of course, I can pinpoint that software change, I take it out, I run a test again, it's fine. It's not that easy on mechatronic complex systems. And also, you have to distribute your test coverage throughout the integration levels and builds. Unfortunately, I've seen it way too often that the component level testers never communicate to the vehicle level testers. So they might run like similar tests or not. You don't know if they have same coverage or anything. So you have to integrate your reporting in a way that the final report takes into consideration everything of that. All right, this is a little software heavy, but if you're familiar with branching strategy, it looks like pretty familiar to you. In order to get continuous validation working properly, you have to have 3 active branches in your software development. The first active branch is the branch your customer has. It has stable code, it is frozen, nobody's allowed to commit any changes there, and it's only open for hotfix. Why do you need that? Because if there's a security issue or if there is a safety issue, you have to be able to release a fix for that issue ASAP. And we're talking hours. Jeff talked about the 0-day reaction time. So in order to achieve that, you have to have a stable branch. Needless to say that all of this does not work if you don't have over-the-air software update capabilities. The second branch is under active validation. So this is where your validation engineers are hammering on and they try to figure out all the corner cases. There's no new feature allowed in that branch and only bug fixes are allowed. And this branch is under change control. So nobody is allowed to commit any changes unless everybody in the organization agrees to it. Then you have the active development branch. This is where your new features are getting committed. It's important to say it's not where your new features are getting developed, because you don't want feature development in your main line. You want feature development in a feature branch. So what you do is you branch out into a feature branch. You start working on your new feature, and you synchronize your feature branch with, or your rebase, every day or every hour, that depends how fast you work, with your main line. So if something breaks, you break it in your feature branch. You do not break the main line, because you have tens or hundreds of feature branches running in parallel here. And if you break the main line, you break all of them. So you continue to work here until everything is validated, verified and validated, and then you merge it back into the main line. And then at a certain point, the branches get promoted, they get ratcheted up. So the customer branch is now this one, and everything moves one up. The important thing is that the validation approach, the continuous regression testing, runs on each and every branch of this. So you don't wait until you ratchet up and your branch is here, and here you start testing. You run continuous validation all the way, all the time here. Of course, depending on the level you are validating. So here's an example. So you have your component level tests, and actually below that you have your unit tests. Unit tests should run with each software commit. At a component level, you start to involve some hardware. When you get some hardware involved, you will have the situation that you don't have faster than real-time capabilities normally, because you're testing on the actual final hardware. But your hill test down here is usually very capable of running a lot of tests in a short time. While when you start to integrate further to a subsystem, it gets more complex, and your tests might take longer. You might even get actuation in place, so you cannot run tests like very fast, one after the other. You have to bring the system back to a start point and then start over. So the tests at the subsystem usually take longer. At the system level, it takes even longer because the complexity of the whole system comes together. You get mechanical interactions, you get electrical interactions, you get some physics interactions in the blade. So you get even more, it's even more effort to run for a full test. So in my example here, if you assume that you have like 100 code commits, and on component level you're capable of testing all 100 code commits, it means you run your test 100 times, one for each commit. On the subsystem level, it takes longer to run the test, so it can only test 40 of those code commits. And then on the system level, you can only test 10 of those code commits. The idea is then that you have to make sure that at least those 10 are tested throughout the entire stack, so that whatever comes out of this test up here, you can hand over to a vehicle test or a test track and say, it went through all of our validation in all the levels. So not that this is here and then wasn't tested here. So in order to achieve that, you have to integrate your test levels with each other. They have to communicate. We had different approaches for that. One is, for example, you tag your software packages. And it's tagged like a tag component tested, subsystem tested, system tested, and so on. And the system is only allowed to pick up software that is tested already on the levels below. It means it might be a little older. I mean, we're talking about minutes, hours older, but at least you have the confidence that is not broken and cannot be has been tested at a level below. Another option is, you have to have some communication queue that the test system down here actually communicates up. So I'm done with that. If you want, pick it up. And it's doing that every time it executes and it finishes. And whenever the next level is ready, it just picks up the last one that's in that queue. So there are tools for that available. You just have to open the barriers and let those different levels communicate to each other. All right, good. Conclusion. First conclusions point in that direction. Integrate your tool chain end to end. So I can't stress that enough. I've seen a lot of teams using automated testing, but what they have is automated test execution. Actual automated testing has no humans involved. It starts automatically, it configures itself automatically, it updates the device under test, it runs the test, evaluates the test, and it reports on the result. That is end-to-end test automation. If there's an engineer sitting on a hill system and is typing all the parameters, flashes the DUT, and then presses start, goes for coffee, comes back, and looks at the result, that is only 20% of the way to go to actual test automation. Run validation as often as possible. So the classic approach is development, then you do testing, then you report the issues, then you fix them, and then you retest. The better approach is you run your validation from the commit 1. You might not get fully passed tests in the beginning, but that's okay, as long as you test the new features. And the point is that the feature developer, they are very focused on their feature. And if they break something in a different feature, they don't see that until they do the final integration and the handover. If you apply the continuous validation methods early in the case, in the schedule, then they can see that right from the beginning before they write hundreds and hundreds of lines of code and figure out that they did it wrong in the first line. Synchronize all levels of validation. As I explained before, the communication between those different levels is essential in order to have the highest efficiency. I've seen very, very, very little good examples for that, and a lot of not really good examples for that. So I suggest to put somebody in charge of bringing all those things together, all those levels. Keep change contests as small as possible, ideally one. So if you manage to implement all of these, then you will be capable to release hot fixes of complex systems within hours and not within weeks or months. That was my last slide. I don't have a thank you slide, but I thank you.